Hey folks, today we are going to start talking about series. And the first half of the series unit, we do something called convergence testing, which basically means that we're trying to determine whether a series converges or diverges. And you should remember these words because when we did improper integrals back in Unit 6, we talked about whether an improper integral converges or diverges. And in fact, there is a specific type of test that deals with relating a series to an improper integral, but that's not for today. So what I'm going to do today is kind of refresh your memory about some terminology about series and then introduce you to the first couple of tests for convergence. So first thing I want to remind you is that a series is the summation of terms in a sequence, and an infinite series is when you're adding up an infinite number of terms from the underlying sequence. So here is notation for a series where we're adding up the first term through the nth term. So this is a finite series because we're going up to the nth term only. It would have to be an infinity here if this were an infinite series. Big S represents the sum of the series, and big S sub 1 is just the sum of the first term. So to get the first term, I plug in this lower index of 1. I get 2 to the 0, which is 1. So the sum of the first term is just 1. Big S sub 2 is the sum of the first two terms. So I take my first term and I add to it my second term. Remember that the domain of the underlying sequence is the integers starting at 1. So my next term, the second term, deals with n equals 2. So I end up plugging a 2 in for this n and I get out 1/2. So S sub 2 equals 3/2. S sub 3, big S sub 3, means I take big S sub 2, which was 3/2, and I add to it one more term, which is the third term, which is going to be plugging a 3 in here, so 1 over 2 squared, which is 1/4. So I end up with 6/4 plus 1/4 is 7/4 when I get my common denominator. So big S sub n is going to be adding up all of the first n terms in the sequence. So 1 plus 1/2 plus 1/4 plus 1/8, all the way up through 1 over 2 to the n minus 1. So let's talk about a typical geometric series, which is a very common type of series that you will see used again and again and again in calculus, and you learned about it first back in Algebra 2. So you had a series, this is an infinite geometric series, where the first term here is a, and r is your common ratio, and it's raised to the n minus 1. And we start at the first term and we go to the infinite number of terms. Or if we started with the lower index of 0, you would just do the first term of a raised and then times r raised to the n instead of n minus 1. So these two, starting at 1 and having an exponent of n minus 1 versus starting at 0 and having an exponent of n, those are equivalent statements to each other. So each term in the series, all you're doing is multiplying the prior term by r, which is your common ratio. So your first term is a, second term is a times r, third term is a times r squared. You eventually get to the nth term, but since this is an infinite series, you keep going. So an infinite geometric series converges when the absolute value of that common ratio is less than 1. That's the same thing as saying that the common ratio is going to be between -1 and 1. And a geometric series diverges if the absolute value of r is greater than or equal to 1. So we're now going to consider the infinite geometric series S sub n. That would be, well, couldn't be S sub n if it's infinite geometric. It would just be S. So if we don't have a subscript there and we just have S, that is the infinite sum or the full sum. So you have a first term of 4, a next term of 4/5, next term of 4/25, etc., and you're adding these together. So the first term is a sub 1. That is this first term listed. That is 4. What is r? R is your common ratio, and that is the number you're multiplying 4 by to get to 4/5. And then you're multiplying 4/5 by it to get to 4/25. So with some simple math here, we can see that our r is 1/5, and to get that, you just divide the term 4/5 by 4, or the term 4/25 by 4/5. So the explicit formula for this infinite series, you could say that each term, a sub n, is equal to the first term times the common ratio of 1/5 raised to the n minus 1. So that is the explicit equation of the underlying sequence. The fourth partial sum is actually just the sum of these first four terms here, and I'm not going to take the time to convert these to decimals and add them up, but suffice it to say that big S sub 4 is just the sum of these first four terms. And then the infinite sum, that's when I'm going to take the infinite series, which starts at 1 and goes to infinity, of my explicit formula, which is 4 times 1/5 to the n minus 1, and I actually want to take the sum of that. Don't forget or recall from Algebra 2 and then from pre-calculus that the infinite sum of a geometric series is your first term divided by 1 minus your common ratio, which in this case is your first term of 4 divided by 1 minus 1 over 5. So that is 4 divided by 4 over 5, which is the same thing as 4 times 5 over 4, which is 5. That is the infinite sum of this geometric series. So here's the deal. A partial sum of a geometric series is this formula, which you might remember maybe being written in a different way, but honestly, we don't use the partial sums very often in this class, so I think we should probably just take it off these notes and not worry ourselves about it. But we do care about this infinite sum, and it applies only if the absolute value of r, our common ratio, is less than 1, and this is the formula that we use, the first term divided by 1 minus r. So let's look at an example. If I ask you to add the infinite sum here plus the infinite sum here, what I want you to do for each is take your first term and divide it by 1 minus the common ratio. So you might have to rewrite the expression of the underlying sequence a little bit to make sure you understand what the underlying sequence is. For this one, it's 2 times 1/3 to the n. And if I plug in n equals 0 for my first term, I get that the first term is 2, and then I see that my common ratio is 1/3. So this gives me 2 over 2/3, and 2 over 2/3 equals 3. So that is the sum of my first series there. My second series, I'm going to rewrite this guy as well. And to do that, I want to have the same exponent in the numerator and denominator, which I can have as n. So if I rewrite this as 2/5 raised to the n, what I have effectively factored out, I've rewritten this numerator as 2 to the negative 1 times 2 to the n, which means that I've effectively pulled out a 1/2 here out in front, which is my 2 to the negative 1. So if I plug in n equals 1, I'm going to get my first term of 1/2 times 2/5, so that is 1/5, and then my common ratio here is very clearly 2/5, so 1 minus 2 over 5. So I now have 1/5 divided by 3/5, and then when I simplify that, I have 1/5 times 5/3, or 1/3. So the sum of these two geometric series added together is going to be 3 plus 1/3, or 10/3 is my overall sum.